All right, so the thing that we want to talk about is, well, first, a reminder. So we've talked about relations in the past, and then we looked at different properties of relations. The reflexive property, where everybody was related to itself, or in our digraph picture representation, those were where we had the loops that were on individual vertices. So the arrow, the directed edge, started at one vertex and came back to that same one vertex. In other words, a length one cycle. We also had irreflexive, which said, nope, you don't have any of those guys. We had symmetric, which said if you have two different vertices, you have directed edges going in both directions. We had asymmetry, which said not only are you irreflexive, you also, if you have an edge between two different vertices, it's exactly one direction. You don't have the two directions like with symmetry. We had anti-symmetric or anti-symmetry, and this was where it didn't matter if the relation was reflexive, irreflexive, or neither. In other words, those little loops on the vertices didn't matter. But if you had two different vertices, you had to have only one maximum of one directed edge between them. You weren't allowed to do the double up. In other words, one-way streets, not two-way streets. We then had the transitive property, which said all length two paths in your cycle. I lie. All length two paths in your digraph have to also be able to be essentially converted into a length one path. In other words, there exists some length one path that starts and ends at the same place the length two path started and ended. Essentially a shortcut if you're thinking in terms of roads. Okay. Now, at that point in time, we talked about equivalence relations. And equivalence relations were reflexive, symmetric, and transitive. And we talked about those guys and we did all sorts of things with them. What we also talked about at the same time is we defined a relation called a partial order. And a partial order was somebody that was reflexive. So to remind ourselves, reflexive here was where you had all of your little loops on every single vertex. Partial orders were also anti-symmetric. So this was where between any two vertices that aren't the same in your digraph, you have at most one directed edge between them. And then we had the same transitive property as the equivalence classes. Not classes, equivalence relations, excuse me. Okay. So that's something that we had before, and we did basically nothing with it. We just defined it. Today, we're going to actually use this thing. So there's something called a partially ordered set, or poset for short. Notice it's kind of an acronym, but not really. The P and the O come from the first letter of partially ordered there. Go figure. But this is simply a set, so it's some set together with a relation, and that relation has to be a partial order. So it's not just the relation, it's not just the partial order. We're really talking and caring about the set, but you can't deal with a set without that relation of the partial order. Okay? So it's the two things in combination, okay, is what a poset is. So what this is in terms of notation, it's often given by something that looks like an ordered pair. This is actually pretty common the higher up in math you get, where you have like some set, then you have some operation on it. And if you ever go into higher level statistics, they actually have it where they've got three things, because they've got whatever their set of objects are and then the different things that they apply to it. But anyway, for us, the first part right here would be whatever set you're dealing with. The second part would be whatever partial order you're dealing with. And a lot of these different posets actually have names. So if they have names, I'll go ahead and put the symbol of the name there. But if they don't have names, we'll put it in this same format of the ordered pair. So let's look at some examples. So the first example that I've got prepped up for us right here says we've got some set. It's going to be a super lazy finite set where you've got just the integers 1 through 5. And the partial order applied to this is a relation that we've checked previously that it was a partial order. Namely, it's the less than or equals to symbol. So if you wanted to write this in terms of the poset notation, you would write it as A, comma, R. Whoa, don't do squiggly. You want to do parentheses there. Or, here's what people will often do, and ignore the set for just now. They'll put the actual symbol for your relation, in this case a less than or equals to symbol, right there for the relation, just so that it's, I would say basically because you're too lazy to write out what the relation is, and you just go ahead and say, hey, notice we're doing a less than or equal to symbol. Okay. If you want to do the shortcut notation that we talked about before when you're doing numbers 1 to 5, the shortcut notation for that set was 5 with a bracket around it. But again, you don't have to do that. You could have just put like A in front of there too. Okay. Now, if we want to look to see if this guy is a poset, well, actually, I lied a little bit. Let's check to see if it's a poset. So check if poset. Now, if we want to check to see if it's a poset, what we need to really check is check if R is a partial order. And I claim this is something similar to what we've checked before, so hopefully it won't be too difficult to check. Okay. The first thing is I'm just going to go ahead and write out the relation R in all of its ordered pairs, not the set builder notation that's currently in this red setup right there. So if we looked at all of our ordered pairs, we have ordered pairs that, and I'm just going to go strategically. If you start at 1, what could be the second position right here after the 1 in one of these ordered pairs? If we want to do the setup, or the way we define this potential partial order as first element has to be less than or equal to second element. So what are our potential second elements right here? Anybody got a guess? In other words, what numbers could I plug into that second slot from 1 through 5? Yep, so in this case, 1's the smallest number in 1 through 5, so it is less than or equal to all of the other ones. So we can just go ahead and say, hey, we've actually got 5 choices here. We could have 1, 1, 1, 2, 1, 3, 1, 4, or 1, 5. I can say that faster than I can write that. Now, if we then strategically went and looked at the ordered pairs that start at 2, if you look at the ordered pairs that start with 2, can you have all 5 of those numbers 1 through 5 in this second slot? In other words, what numbers can we put in this second slot if the first position is a 2? Right, you can't get them all. So which ones could you do? You could put in 2 through 5. So we'll have here 2, 2, 2, 3, 2, 4, 2, 5. And if we started with 3, what are the numbers we could put in that second slot for 3? Yep, so this would be 3 to 5, so we'll have 3, 3, 3, 4, and 3, 5. What about if the first slot was a 4? So that would be 4 and 5. So we'll have 4, 4, and 4, 5. And last number that we could start off our ordered pair with is a 5. What could we plug into the second position if we started with a, yep, it'd be just 5, 5. Now, if we then, oh, I can't go up. If we then look to see if this guy is a partial order, and let me put the work right over here to the side because let's face it, I didn't leave myself enough space. So here, if we look at reflexive, what do you guys think? Is this relation reflexive? So you're looking for all of your ordered pairs where both positions are the same. So here you've got 1, 1, you've got 2, 2, where'd it go? You've got 3, 3, you've got 4, 4, and you've got 5, 5, or just look at the equals in the formula up top. This guy's definitely reflexive. Now, what do you think about anti-symmetric? In terms of the digraph, anti-symmetric means you've got one directed edge between 2 different vertices. But in terms of the ordered pairs, what are you looking for? Well, you're looking for, if you have 1, 2, that you don't have the reverse. In other words, if you flip-flopped this ordered pair and wrote 2, 1, you don't have that one. So let's check them. So you ignore the ones that are doubled up. So if you have 1, 2, do we have 2, 1? Do we have 3, 1? Do we have 4, 1? Do we have 5, 1? What do you think? Do we have any of those 4 guys? Right, so we don't have any of these four guys, and it's not sufficient to just check the first four. You'd also have to check the next ones as well. But if we go and we check these next ordered pairs, it does turn out that when you flip the order of the ordered pairs, you won't have the other ones as well. And you can actually see that from up here in the formula as well. If you flipped this inequality, or if you reversed, I guess it's probably better to think of it over here. If you reverse the A and the B in the ordered pairs, would this inequality automatically be flipped? Well, not if you started off with knowing that A and B were less than or equal to each other. The only one that would still work would be if A and B were actually equal. So in this case, we'll still get the anti-symmetry. And I'm just going to tell you it's transitive. I'm not actually going to go through and check it because that one is a pain in the butt to check. So this here is actually a really, really classic example of a partial order, and put it together with its set would then be a poset. And that's all you do to check if somebody's a poset, is you just check to see if the relation on the set you're given, so in our case the R, if it was a partial order. So that's it for that one. Now the next one we've got, next example I've prepped up for us is also a super duper really classic example of somebody that's going to turn into, if you look at both the set and the partial order together, a poset. The relation itself is going to be a partial order. So if we wanted to check to see if this next example, this example labeled with a B, actually is a poset, the thing you'd want to check is the relation itself, this R guy, actually in partial order? Okay. Now, I'm not going to lie, this is actually the not quite standard way that people write it. Here's how people normally write this. The set A is written normally, but the relation R here, people typically go ahead and use that condensed form for the poset notation. So you've got A and R, and what people will say is they'll say, hey, A is really some power set of the two elements A and B, and then relation R is given by set inclusion, is how it's read. In other words, you're finding subsets. Okay? So this relation R says, hey, two elements, so two of our sets from the subsets of AB are going to be related to each other if the first set is a subset of the second one. And it doesn't have to be proper. It's okay if they're equal to each other. So here, if we wanted to check to see if we had a poset, we'd check to see if R is actually a relation. Before we do that, we need to know the elements of A that we're working with. So here, if we wrote out the elements of A, remember the notation up here says means power set, and we said you could remember either when you wanted, so I went back and put the two versions of writing a power set. This power set says look for all the subsets of the set AB. So we have the empty set, we have the one element sets of just A or just B, and then we have the full set itself. So there's actually only 4 elements of that power set, which means we can now go ahead and write out our relation. And here, you could say, if you did it in order by cardinality of your subsets, you could start maybe with the empty set. Well, if the empty set is in the first slot, according to the formula for the relation, your second slot is going to be all the sets in A that B is a subset of. Well, B is the empty set. It's a subset of everybody. So we could write, hey, here next, just another empty set, as I almost forgot it. We could say empty set, and then just the set A, empty set, just the set B, empty set, and the full set AB. Notice it looks really similar to what we did in the last example. Now, next move up, we go ahead and grab one of our one element sets, maybe the set of just the element A. And here's where things get a little different, okay, than the previous example. So here we've got the rule for our relation says the first element, first position, is related to the second position for what? Little set here that's only of A has to be a subset of whatever we write next. What do you guys think? Who has little a as its subset among our 4 possible choices? Hint, it's not all of them. Anybody have a guess on what sets have that one element set consisting of A? Yep, there's two of them. One of them is the set itself, and the other one is the full set that includes both A and B. Halfway done, although not really. While we're halfway through the positions, we actually are less than halfway through in terms of what we're going to write down. Any guesses what ordered pairs we can form where the one element set formed from little b would look like? In other words, what can we put in this second position right here if our first position is that set comprised just of lowercase b? Yep, so it would look almost identical to the last two we wrote. So we would have BB, and then we would have, pretend that was a parenthesis, B and AB. And then the last type of ordered pairs is where your first position is the full set AB. Any guesses what that last position has to be? In other words, AB is a subset of who? And your only choices are these four from set A. So AB lives inside of which of those four sets? Yep, last one and only the last one. Here is AB. This guy is actually so special, it actually has a name. This one here, we'll go ahead and check real quick if it's a partial order. We're going to find that it is. And the combination of the set with this particular partial order has a name, and its name is B2. And we'll see why that is. Probably not today, probably next week. Okay? But just to give you that information. Now, my claim was that this guy is a partial order, which means it should be reflexive, anti-symmetric, and transitive. So what do you think? Does it look like it's reflexive? Do we have four ordered pairs, each of which is each of the four elements from set A in both the positions? In other words, do we have empty set, comma, empty set? Do we have A, comma, A? Notice I'm not reading off the curly braces. That's only because I'm lazy. Do we have B, comma, B? Do we have AB, comma, AB? We do. So that means this guy is totally reflexive, and that also comes from our formula right here. Notice the little equal symbol on the bottom. So that means we're going to include all of those reflexive ordered pairs, which means we'll get the reflexive property when we get all of them. Now, anti-symmetric, we talked about anti-symmetric in the last example. So what do you guys think? Does this guy look like it's anti-symmetric? The only place you have to look is the non-reflexive ordered pairs. So there's, what, 6 of them that you got to check. So in this particular case, if you take the 6 non-reflexive ordered pairs, so these 3 right here, so ordered pair number 2 through 4, and then this guy, so what is that? Ordered pair number 6, and then the 2 right before the last, I lied, the 1 right before the last one, so only 5 of them. If you flip-flop the ordered pair, it turns out it's a new ordered pair, but it's a new ordered pair that's not in our relation, which means we are anti-symmetric. And just like in the last example, I'm just going to go ahead and tell you that this guy turns out to be transitive because I am too lazy to go and check it right now. Okay. So that would be some examples of things that are actually posets. Now they're posets once you start dealing with the set itself with the partial order attached. Okay. So that's sort of the idea of these poset guys. And that's it for those examples. The next thing that I want to talk about is building the picture representation of the posets, and this is going to be called our Hosta diagram. It's basically our digraph of a relation that we've had previously, but with some of the extra pieces and parts removed because they're, let's face it, going to make our picture more complicated than what we wanted. So here's what we do. So the Hosta diagram you have to first have a poset. So if you don't have a poset, this structure is not going to work out. And in terms of how to create this Hosta diagram, if you already have the digraph of your relation. Now, for many of our relations, I shouldn't say that. We know how to create digraphs of relations. So you actually could, I'm not going to recommend this, but you could always take your relation that you're given, your partial order, create the digraph associated with that partial order, and then do this method for converting the digraph into a Hosta diagram. That being said, unless you're dealing with a really small set, there is a faster way to do it, and I'll show you guys that faster way of getting directly to the Hosta diagram without going through the digraph after I show you how the Hosta diagram is formed. Okay. So first thing that you do is you go ahead and you've got your digraph. Okay. So assuming we already have that, we're going to remove all of the loops in the digraph. Now, why would we remove all of the loops in the digraph? Because we're dealing with partial orders. Partial orders as relations are always reflexive. So this means what? This means that we always know there's going to loops here. This is because partial orders are reflexive, just by their definition. So that means behind the scenes, we know for sure all those loops are really there. This is the same idea behind, think back to like an algebra class, where you might write 1 times x. It's not wrong. It's perfectly fine to do, to have 1 as a coefficient. But in practice, what do? You don't bother to write that 1 out front. Why? Because everybody really knows it's there when you just see an x. That's the same idea here when you're dealing with your partial orders. Now, the second thing that you do is we're going to remove all of our transitive edges. Now, I put in quotes transitive edges here simply because that's not their real name. They don't really have a real name. But here's what we're talking about. Let me draw the picture. So in the digraph, something like a transitive edge would be this. You've got some vertex, an edge to a second vertex, an edge to a third vertex. That guy is your transitive edge. Okay. So what we're going to assume is if you can travel along any path in your digraph, we're going to take off the shortcut ways. Okay. Why? Because what we'll say is instead of being stuck to only travel along one edge at a time, we know that if we can get from vertex A to vertex C, regardless of the length of path, we really could have gotten there in 1 step. Okay. So this is a little bit more fancy in terms of what we're removing. Okay. But the reason that we can remove this, those highlighted edges, is, again, because all of our partial orders are transitive. And I'm going to abbreviate that just because we're about to run out of space. Now, the last step, you really could break it into 2 steps. What it says is we're going to reorient all of our vertices so that all of our directed edges, all of our little arrows are going to point upwards. They don't have to point straight up. They can point at a slant. So you want to do this. So they're either going to point up like that or maybe they're slanted. Okay? There's definitely cases where you have to have the slanted arrows. Okay? Once you've gone ahead and rearranged all of your vertices so that all of your arrows are pointing in an upwards direction, either they'll look specifically vertical or they're slanted where the arrows pointed upwards. You're not allowed to have any horizontal lines or any arrows pointed down. Once that's changed, then you go and you erase off the arrowhead of your arrow. Okay? In other words, you convert the directed edge that has the arrow to an undirected edge that does not have the arrowhead. Okay? Now, that's the procedure for converting a digraph into a Hosta diagram. So let's look at this with a very small example to see what happens. And I'll go ahead and title what we're doing at each step here. That way you don't have to remember the top because we're not going to be able to see it when I pull this example down. All right, so for this guy, our set A is simply the letters A, B, and C. And the relation that we've got is given by the ordered pairs AA, AB, AC, BB, BC, and CC. Now I'm going to claim that this guy is already a partial order, or the relation is already a partial order, but notice we can see that relatively straightforward. We have here AA, BB, CC. There's the reflexive property. For the non-doubled up pairs, AB, we don't have BA, AC, we don't have CA, and for BC, we don't have CB, so it's also anti-symmetric. And just like before, I'm going to skip out and just tell you that yes, it's actually transitive too. So first thing, let's go ahead and draw the digraph. Actually, we could probably have seen all those properties much easier in the digraph. I should have done that first. Oh well. So here's our digraph. Or technically speaking, it's going to be our directed multigraph. When you just say digraph by default, people normally assume that you are not talking about a multigraph. In other words, that you don't have loops. But we do. So we've got our three vertices from our three elements of set A. We've got AA, so loop at A. We've got AB, so directed edge A to B. We've got AC, so directed edge A to C. We've got BB, so loop at B. We've got BC, the directed edge from B to C. And we've got CC. So notice here it's now easy to see that it's reflexive. You've got loops in all the vertices. It's easy to see that it's anti-symmetric. Any two different vertices has at most one directed edge between them. And transitive, it's actually easy to see transitivity too. The only length 2 path that doesn't include loops is A to B to C. And we've got the shortcut A to C right there. So it's transitive as well. Now, first step that we're going to do to grid our Hosta diagram is we're going to remove all the loops. So if we take this same picture and we remove all of the loops, what do we have? Well, the new snapshot, and I'm going to scale it down just a little bit so I don't run out of space here. We've got AB, or A to B. Down here at C, we've got the 2 directed edges that come down to C, and notice all the loops are gone. Now, the next thing that we want to do is we want to grab or remove any of our transitive edges. So step 2, remove transitive edges. So in our particular case, a transitive edge, the only one in this picture is actually A to C. Why do I know A to C is our transitive edge? Because this was the guy that was the shortcut of our only length 2 path. So anytime you have a length 2 or longer path, if you have a shortcut way to get there, those are the edges you start removing, the shortcut edges. So here, and I'm going to move the picture over to the side so it doesn't get too bunched up. Over to the side here, we still have the A, we still have the B, we still have the C, but now we only have 2 edges, left in the picture. Now, last step says, as needed, reorient your vertices so all of your edges, all of your directed edges, have their arrows pointing up. Do we currently have all of our arrows pointed in an upwards direction? We do not, so we're going to have to reorient these guys. Orient, so arrows are all pointing up. So in this particular case, what are we going to do? Well, we've only got 2 arrows. They both need to be pointing up. So this one is actually going to turn out to what looks like a straight line. So we'll have here, looks like what? A should be on the bottom. Then we'll have an arrow that points straight up to B. We have an arrow that points straight up to C. So that's the reorient. You move your vertices around so that they're in a good position so that all the arrows will point up. And you would prefer all your arrows to point up in vertical little arrows with the arrowhead at the top. But sometimes, especially in much more complicated posets, not the one we are currently working on, you'll get where maybe you can't go straight up. Maybe you have 2 guys at this same level as C, and you actually have to do slanted lines. Okay. Now, this is not the finished product. Our finished product, and I'm going to go ahead and put it over here as 4. The actual Hosta diagram is, any guesses what the last thing is that we need to do? Anybody remember? there was one last thing to do after we reoriented the vertices. And I know I told you you didn't have to remember these steps, so I was going to write them down. Did anybody happen to remember the last step? Yep. The last step was actually to remove the arrows. Notice, once you reorient so your arrows are always pointing in an upwards direction, you don't need the direction anymore because you know you're always going to follow the lines from bottom to top. So you're always going to travel bottom up. So the actual Hosta diagram of this particular poset literally has 3 vertices all lined up, all stacked on top of each other, 2 undirected edges, so no arrows anymore between them. So that would be the final answer here for this Hosta diagram. Questions on the procedure kind of make sense so far. Kind of is the key word here. That's it in terms of making a Hosta diagram. This procedure will actually work for almost any poset you have. The only issue with the almost is if you have an infinite poset, but we're really not going to play around with infinite posets in our class. So as long as you have a finite poset, this method would work. Now, you may not want to use this method when the posets get more complicated. You have more elements in your building set A, and I'm going to show you an alternative or shortcut way to get to this same picture at the bottom right there. Okay. But this method right here that we've just done, this will work all the time. Now, before we go on to some extra examples of building Hosta diagrams and me showing you the shortcut, a couple definitions. The first thing is something called comparable. And this refers to elements. Okay? So suppose you've got some poset. It's in whatever poset you want. So you've got some set, whatever it is, some partial order, some relation right here, whatever it is. If you pick any 2 elements in your set, in your poset, and typically people will pick 2 different elements because this always works for sure if the 2 elements were really the same element, but you could pick the same element. So suppose you have 2 elements. These guys are called comparable if one of them is related to the other. And it doesn't matter the order of that ordered pair. So just as a reminder, in terms of notation, this first one means in your relation you have A comma B in the relation, and that second one means you have B comma A in the relation. Now, since your poset or your partial order is anti-symmetric, you know you wouldn't have more than one of those 2 ordered pairs in your relation. So this says you have one of these 2 guys in your relation, you don't have none of them in the relation. Okay? Now, we needed that definition, both because I believe some of your homework questions talk about, but really more because we wanted to talk about the definition of a chain. So a chain is a poset whose Hosta diagram, you're going to love this, literally looks like a chain. Okay? I'm sure that's where the name came from. Its formal definition is it's some poset where every pair of elements in your building set are comparable. Okay? But in terms of if you have the Hosta diagram, I'm going to claim that this guy right here is totally a chain. I can recognize that because it literally looks like a physical metal chain. Why? You've got your little blobs right here, and they're connected together with links. I realize blob is not a technical term. Okay? So your chains, they can be various length chains. This one here has 3 vertices or 2 edges in it. You can have longer chains that have more vertices and more edges. It's hard to have much of a shorter chain. A shorter chain would have 2 vertices, 1 edge, and past that, you're probably not going to care in terms of shorter. Okay? So this guy here is talking about a change, and this comparable thing means if you take A and B, well, A here is related to B. If you take A and C, well, A is related to C by way of the transitive edge we removed, or because you can travel straight up the chain. If you looked at B, B is comparable to C because B is related to C by way of that edge right there. And that just tells you that, hey, any pair of elements, and I just picked the different pairs of elements, would be comparable to each other. So that's the idea behind a chain. And often people will do things like CN for the name of the chain, just C for chain. These guys are actually relatively boring to work with, but honestly really nice to have too. It all depends on what it is that you want to work with. Okay. So the next example that I've got for us looks similar to one that we've done before. This is a classic way of setting up this particular guy, and I'm going to claim that it is a poset. So I'm not going to go through showing that our relation here is a partial order. I'm just going to tell you it is a poset. And in terms of this guy, not mean for that to be green. Let's pretend we didn't do that. This guy, it has a name. Its name is B3. And in terms of if you wrote it in that ordered pair notation, the building set that we have here is set A. So this is the power set of the set 1, 2, 3. And the relation or the partial order is given by set inclusion. So this is very similar to that example we did back on the little set A, comma B, where we found the power set and then we went and we found all the ordered pairs. Well, I'm not going to do the ordered pairs in this case, okay? But we're still going to build the Hosta diagram. Oh, awesome, I already gave us the name. There's me forgetting what I wrote down previously. So here's a shortcut way where you don't have to write down the full digraph. You can jump straight to the Hosta diagram. So key thing is looking at your partial order. Our partial order right here is defined by set inclusion, or if you prefer, in the actual formula of the partial order right there. And what that means is what? It means the guy in the first position, or the set in the first position, is going to be inside of, or a subset of the guy in the second position. In terms of arrows, what is this telling us? Our arrow starts at set B and ends at set C. That's how our digraph would be put together. What do we know about our partial order? At the end of the day, all of the arrows need to point upwards. So we need to find the smallest set that's inside of everybody else. So what we're going to do here is we're going to stack, or we're going to organize our power set, our building set A, our power set of the set 1, 2, 3 in terms of cardinality. So if we think about smallest, that would be the smallest cardinality. Any guesses who the set is that has the smallest cardinality in this power set? Anybody have a guess? Yep, it'd be the empty set. So what we're going to do is at the very, very bottom of our Hosta diagram, we're going to go ahead and put the empty set. And I'm going to label to the side here what I'm doing. So this guy here has cardinality 0. Now, the empty set is a subset of every other set in your power set. But remember what we also did when we built our Hosta diagram. We removed the transitive edges. So that means we're in terms of the edges that are going to be attached to the empty set here, we're not going to jump across several other elements, several other vertices. We're only going to keep the ones that directly touch somebody. And I realize that was perhaps not clear whatsoever, so let's just get to our next level to do this. So the next set that's the next size bigger would be sets of cardinality 1. How many sets of cardinality 1 do you think there are in this power set? That way it's easy to type. So there'd be a grand total of 3 sets with cardinality 1. It's just all the individual elements. So this would be the set, I'm going to line it up with cardinality 1 over there. The set only consisting of the number 1, only consisting of the number 2, only consisting of the number 3. So I'm going to build this Hosta diagram in stripes. Okay, so those are all the cardinality 3 guys. I lie, cardinality 1 guys. So quick check, is the empty set a subset of all of those sets? Don't overthink it. Is the empty set a set of all of those 3 new sets? The empty set's a subset of every other set. So we're going to go ahead and put in our edges. Now, if we were building a digraph, we'd put in arrows, and the arrows here would all be pointing up because the empty set is the subset of the other ones. However, in this case, those arrows are all pointing up. So in our Hosta diagram, we're not going to need the arrows, so I'm just going to draw them in straight lines. And that's it for right now. That's all we can do. Now, if we look at the next sets in this power set, the next size bigger would be cardinality 2 subsets. So any guesses how many cardinality 2 sets are going to be in this power set? Ooh, it's not 6. Much smaller. It would actually be 3. So we've got 1, 2. We've got 1, 3. And we've got 2, 3. And here's a fun fact now that we've done combinations. You can tell how many you're going to have at each level. Here, we started from a building set of 3 elements. The number of sets of cardinality 2 is going to be 3, choose 2. Number of subsets with cardinality 1 is 3, choose 1. Number of subsets with cardinality 0 is 3, choose 0. Oh, yes, don't do the doubled up ones. It's a proper set, not a multi-set. So that would totally account for the extra numbers you had then. All right, so let's incorporate these 3 new subsets. So first thing is, let's just look between the level of cardinality 1 sets and cardinality 2 sets. If we look at this set just comprising of the number 1, it's a subset of 1, 2. It's also a subset of who? Yep, it is also a subset of 1, 3. And then you do the same thing, subset of 1, 2. 2 is also a subset of 2, 3. And if you look at the element 3, it'll be a subset of 2, 3, and then also that 1, 3. Now, here's where we're going to drop a row. Okay? So we have dealt with everything between the second row and the third row that we built. If we drop down to the first row that we built, is 0 a subset of the 3 newest sets? Yes, it totally is. But if you tried to add in, and I'll put in a different color here and then we're going to erase it. If you tried to add in the line of the empty set up to 0, 3, that is totally correct in terms of the empty set being a subset of the set 2, 3. However, that red edge that just got inserted should not be in the Hosta diagram. And I guess that's why I say we need to remove that red edge from the Hosta diagram. It's fine in the regular digraph. Yep, so this guy here was one of those transitive edges, one of those shortcut edges. So it turns out if you're in these type of Hosta diagrams, the examples that I'm going to show you are, there's a buzzword for it. It's actually called a graded poset. And what it means is you're able to insert it in terms of stripes. So you check jumping between levels right here, is that really a transitive edge? And the answer is always going to be yes for this example and for most of the examples we're going to do. So you wouldn't insert any edge that actually is one of those transitive edges. Or transitive isn't a real word. Transitive edge. All right, so we've got one more set to add in, and the last set to add in is, oh, did not mean to do that in red. The last set that we're going to put into our picture or our Hosta diagram is our full set. This is when we use all 3 of our building elements from that set S. In other words, we're going to put in set S. So numbers 1, 2, and 3. Now, every other subset in the picture so far is a subset of this set. That's the definition of a power set. But we're not going to have lines coming from all 7 of these other guys. They're only going to come from this top stripe. So 1, 2, 1, 3, and 2, 3 all will get lines up to the set 1, 2, 3. If you did try to put in a line, say from 1 to that new set 1, 2, 3, notice that is again one of those transitive edges that you don't want to include in the Hosta diagram. So I'm going to go ahead and remove that from the picture. And that, with no adjustments whatsoever now needed, is your Hosta diagram for the poset B3. Questions make sense, kind of feeling a little bit okay. Can at least follow it if somebody else does the work. I'm going to assume that means sort of. Okay, so this is an example dealing with subsets. Let's look at another example. So the next example that I've got picked up for you, and if it helps, something interesting about this particular example we just finished, the Hosta diagram right here, if you sort of squint at it, totally looks like a cube. The thing that happens with these types of posets up there. But we'll talk more about that later. So the next example I've got prepped up for us is also a pretty classic example. This guy has a different set that you start with. Here we're not dealing with the elements of our set being subsets themselves. Instead, we're just dealing with a building set A of numbers. And this happens to be all of the factors, all of the positive factors, or as is typically said, all of the positive divisors of the number 18. So that's the building set. The partial order associated with this guy is this guy right here. And if you recall, what does this mean? This symbol is, wow, that was a terrible circle. Pretend I could actually draw a circle. Slightly better. That's read as A divides B, or A is a factor of B. Most people like it better if you say A is a factor of B. So the poset that's put together is that building set of the divisors of 18 in conjunction with the relation where the first coordinate, the first slot, is a factor of the second slot. Okay? The actual poset itself is those two things put together. And this one actually has a name. It's capital D with a subscript 18. D stands for divisors. The 18 tells you which number you took the divisors of. Now, if we wanted to write out the complete partial order, I really don't want to. But it would be things like this, just to remind us of how this would go. You would have 1, and 1 is a divisor of everybody else, or a factor of everybody else. So you'd have 1, 1, 1, 2, and it keeps going until you get to 118. But then when you get to 2, you'd have 2, 2, 2, 6. Totally typo there. 2, 6, 2, 18. And then when you get to 3, I'm going to stop at 3. So 3, 3. Well, this one actually has a lot of them. 3, 6, 3, 9, 3, 18. So notice there's a lot of ordered pairs that are going to start happening here, which is why I'm not writing them all out. So just like with the other one where you get a lot of ordered pairs, instead of starting out with the digraph for this particular partial order, instead we're going to jump straight to the Hosta diagram of the poset. But we're still going to need to figure out structure here. So notice this now is dealing with the factors of your various numbers. And one of the tricks in this type of poset, specifically where your partial order deals with division, the trick is to write all of your building elements, all of your numbers from your set A here, in terms of their prime factorization. Okay? Well, 1's not prime, so it can't change. 2 and 3 both are prime. So when you talk about prime factorization, we're really only saying we're going to rewrite the numbers 6, 9, and 18. So if you write 6 in terms of its prime factors, what would be the prime factors of 6? Or the prime factorization of 6? Yep, it'd be 2 times 3. Anybody got it for 9? So this one here would be 3 squared. Anybody got it for 18? So this one would be 2 times 3 squared. So we're going to build our levels of which numbers we're going to pull in as we put them into the Hosta diagram based off of their prime factors, and specifically based on how many prime factors they're going to have. So let's see if we can't scooch this down just a hair. Oh, I'm going to have to just shrink it. All right. Not quite good enough. All right, I think that works. All right, so in terms of these guys, when you're dealing with prime factorization or division or factors, 1 is always the one you put in the bottom. Why? Because the number of primes in its prime factorization is exactly none. That was trying to be a 0. So then that's the only guy with no primes. Then we look for a prime factorization where there's exactly 1 prime number in the prime factorization. In other words, the first level up from the number 1 is always the listing of all of your prime numbers. So in our case, who are our prime numbers? Don't overthink it. Prime numbers from set A is, or are, because there's 2 of them. Hopefully you are all thinking 2 and 3. So our prime numbers, we've got 2, we've got 3, and we just write them down. So far we've used 1, 2, and 3. We still have to put in 6, 9, and 18. So this is where we start looking now at the edges that can go in. So is 1 going to be related to 2? Well, sometimes that's difficult to think of in terms of that way. So go back to your relation, your partial order, and you're looking for factors. So you reword this as, is 1 a factor of 2? What do you guys think? Is 1 a factor of 2 or 3? Yep, it's actually a factor of both of them. So we're going to put in both of these lines. Technically in the digraph, you'd have arrows pointing from 1 to 2 or to 3. Since we're building a Hosta diagram, we're just going to make sure the 2 and the 3 are above the number 1, and that means our orientation of our edges is correct. Okay? That's all we can do at this point. So the next thing up is where we look at it, prime factorization of our numbers, where we have exactly 2 prime numbers in our prime factorization. And so if we look at the 3 integers left, the 6, the 9, and the 18, which one or ones of these guys have exactly 2 numbers in their prime factorization? Can anybody spot one of them or all of them? Looking for 2 primes in the factorization. Or 2 factors in the factorization. 6 is definitely one of them. I'm going to put the 6 on top of the 2. Turns out there's one more. Anybody spot the one other number that we're going to use? It would actually be 9, and this is because even though 3 times 3, both of those prime numbers are 3, we're not counting distinct primes, we're counting how many factors of primes we have. So 6 and 9 would be your 2 guys that have a prime factorization dealing with 2 primes. Notice I didn't say 2 different primes. Okay. Now we're going to go ahead and incorporate those 2 numbers, 6 and 9, into our Hosta diagram, or at least what we have so far of our Hosta diagram. So we're going to go previous strip that we put into the Hosta diagram first, and then we'll look at anything below that previous strip. So what do you think? Is 2 a factor of 6 or 9 or both? So the question is, who is 2 a factor of between 6 and 9? It is a factor of 6. It is not a factor of 9. So we're only going to go ahead and put in that one edge. And notice in terms of the poset, the arrow here would be pointing straight up. So that means we've done good. I'm just not going to put the arrowhead on top. Now when we go over here to 3, we're going to ask the same question. Is 3 a factor of 9 and or 6? What do you think? Is 3 a factor of either 9 or 6 or both or neither? Yep, so 3 is a factor of both of these two guys, so we're going to put in both of those what in the digraph would be arrows, one pointing vertically up, the other slanted. And this is how you're forced to have slanted arrows because you can't have 2 arrows pointing directly straight up. Okay. Now, since we're building a Hosta diagram, we just don't put the arrowheads in. Now, last check is we're going to check to see if 6 and 9 need to have any edges between 1 and either the 6 or the 9. And I'm going to claim that technically, yes, 1 is a factor of both 6 and 9. I'm going to go ahead and put it in the edge here at 9. But why would I say that edge that I just put in red from 6 to 9? Well, technically in your digraph is not going to be in your Hosta diagram. Why would that red edge not be one we want to include in the Hosta diagram? Yep, so this one here is same reason that we had some edges we didn't include in the last example. This is one of those transitive edges because we already have a length 2 path from 1 to 3 to 9. So that's that shortcut transitive edge that we are excluding from our Hosta diagrams. In other words, to make the picture less cluttered. So I'm going to go ahead and remove that edge. Now, there's only one last number that we haven't used yet from our building set A, and that's the number 18. So 18 has 3 primes in its factorization. So I'm going to go ahead and write 3 primes right here. So I'm going to go ahead and make sure that it is above everybody else. Okay? Now, just like with the last stripe, we're going to check first with how 18 connects to the line that includes the 6 and the 9, and then we'll make sure that there's no extra edges we need to pick up from the elements below. So, what do you think? Is 6 and or 9 a factor of 18? It could be none, 1, or both, and yes, the answer is both. So we'll go ahead and put in both of those 2 edges. And in the digraph representation, these would totally be edges pointing to 18. However, in the Hosta diagram, we're not going to put those arrowheads on. Now, quick check. If we look at 18 and the numbers below 6 and 9, so the 1, the 3, and the 2. Are 1, 3, and 2, wow, I did that wrong. 1, 2, and 3, are all of these guys or are any of these guys factors of 18? Right, so all of these guys are factors of 18, which means in the digraph, you're going to have an edge that goes from 1 to 18, 2 to 18, and 3 to 18. I'm going to go ahead and put in the 1 to 18. But I'm going to claim that in the Hosta diagram, we don't need any of those 3 edges. Any guesses why we don't need any of the edges of 1 to 18 that's drawn in red, or 2 to 18 or 3 to 18 that I didn't draw in? You got it on the primes to 18 because this is properly a length 2 path and then 1 edge. But it turns out that this 1 to 18 edge is also one of those transitive edges, even though this is a length 3 path and that's your 1 to 18 is the shortcut. It turns out when you start adding in the new transitive edges, this would be one that would need to be added in, not in a first sweep, but second sweeps. Okay. But either way, one of those transitive edges, one of those shortcuts to your paths of length 2 or bigger. So you don't need, you don't need either of those 2 red lines, so I'm going to remove them. So this, where it looks kind of like a hexagon with 1 line through it from 3 to 6, that would be your Hosta diagram of D18. So I'm going to go ahead and label this one. Did not mean for that to be in red. That's it. Those 2 examples are sort of the quintessential examples on how you build Hosta diagrams without bothering for the digraph first. Any questions before we move on to the definition of isomorphic posets? Procedure kind of makes sense? Basically, you're going to look at whatever your formula is in your partial order, figure out how you can break that up. So like when we did subsets, we looked at the size of the set. When we did factorization, we looked at the size of the prime factorization. Okay? So how you actually add in these stripes of elements to your Hosta diagram does depend on what that formula is. All right, I'm not seeing any questions come in, so if you come up with one, definitely feel free to ask them. I'm going to move on to the definition of isomorphic posets. Now, I went ahead and prepped up the very, very official definition of isomorphic posets, and then we're going to do the interpretation of what this really means. Okay? So, when you have posets that are isomorphic, it turns out that only occurs if you have a function between them that's called an isomorphism. So we're actually going to have two definitions in one. So you start off and you have two posets. So poset number 1 here has its building set, set A, and its partial order of R1 because I was too lazy to come up with a better name. Partial order number 2 has a building set of B, and the partial order right here is R2. Again, I didn't think of a better name when I was prepping this for you late last night. Okay? But we're going to say that those two guys are posets. Now, suppose you've got some function f, and the function's domain here is the set A, and its range is the set B. Okay, so you plug in elements from the first poset, you'll get back elements from the second poset. And the claim here is that we're going to go ahead and let this guy be a one-to-one correspondence between our two posets. And remember, a one-to-one correspondence means what? You plug one number, that's a good way of thinking about this. I'm trying to think what math courses you guys would have had in the past. You should have all had some sort of algebra class where they talked about one-to-one functions. One-to-one functions, so here's a little to the aside. If you graph your one-to-one functions, this is where you have the horizontal line test if you're the one-to-one. Okay? So it says if you have any outputs, there's exactly one input that gave you that output. So that's your one-to-one. Now, here's what this says. It says, hey, this function is going to be called an isomorphism. That ending of ism, the ISM, refers to a function in math. So this guy is going to be called an isomorphism between the two posets if little a and little b are related to each other in the first poset, then you better get in the second poset that the two outputs, so f of a and f of b, also are related to each other. And remember, with the R in the middle means you've got the ordered pairs. So this guy here is exactly the same thing as saying AB is inside the relation in the first poset. Exactly when you run A and B through your isomorphism through your function, you get back whatever the elements you correspond to in the second poset, and those two guys are related to each other. That's what that means. Now, that's a fair amount of theory to get to the following fact. If you've got this function that does those things, then you call the two posets isomorphic. We're never going to use the function. Okay? Here's what you actually need to know. In other words, what this means. This means that your two posets are isomorphic, and the symbol here for isomorphic looks like an equals with a little tilde up top. Isomorphic posets or isomorphic structures, if you're in some other topic, what it means is it's two things that have the exact same structures. The only thing that has changed between these two objects is maybe you change the labels. So in our particular case here, if you've got these two posets and they're supposed to be isomorphic, maybe their posets are defined differently, maybe their elements in their building sets are defined differently, but they have the same structure. And for us with posets, that corresponds to when we build the Hosta diagram. The Hosta diagrams will look identical barring labels. So if you erased all of the labels, the structure would look identical. So let's look at an example. And when we get through this example, we're probably going to be close to the end of class time. So the example that I've got for us, I wanted to keep that name. The example I've got for us goes as follows. We've got a building set of the numbers 1, 2, 3, and 6. So these are all the factors of 6. And we've got a relation right here that says, hey, any two elements from this building set are going to be related if the first element is a factor of the second element. This is, or this has, a name. This guy is exactly the same as D6. So this is factors of 6. And then that relation was that is a factor of, if you will. Okay. Now the second poset right here, this is actually one of the ones that we did at the very beginning of class, so we already know what that one looks like. Ooh, actually, that means I might be able to label something, one definition at the end today that I didn't think I'd get to. This is the same as our B2 from earlier. This one was the one where it was the power set of the set AB ordered by set inclusion. Okay. So let's go ahead and see if these two posets are really congruent, not congruent, wrong word, not applicable right now. See if they're isomorphic to each other. So what I'm going to do is I'm just going to use this interpretation up here of what isomorphic means, which is we'll build our two Hosta diagrams, and then we'll see if the Hosta diagrams look the same. Now, for this guy, while we looked at him as a poset earlier, I don't believe we actually built his Hosta diagram, so we'll need to worry about doing that. The nice thing about both of those two examples, or both of these two examples, is they look very similar but are smaller than the two examples we just finished building. I'm going to use the exact same techniques that we used on the two examples we just finished building. So starting with poset number 1, or D6. Okay? We've got exactly 4 elements in the building set, the 1, the 2, the 3, and the 6. 1 always goes on the bottom because it has 0 prime factors. So 0, wow, that was terrible size, 0 prime factors. Then we look at our primes in the set. We have 2 of them. That's 2 and 3. So this is 1 prime. And then we only have a 6 left, so this one, even if you didn't do its prime factorization, you can look to yourself and say, hey, it's not prime. Let me look to see how many prime factors it has. And we said previously, when we looked at our other example, 6 was the same as 3 times 2. So it goes up here on top as 2 primes. And I probably should have gone back and put in the edges before I put in 6, but I forgot to. So let's start from the bottom and go up. So 1 is a factor of everybody else, but don't put it in for 6 yet. Okay? So 1 is a factor of the 2 primes, 2 and 3. If we then look at the second stripe, the prime numbers, both 2 and 3 are factors of 6. And I did a warning before of don't put in that extra edge from 1 to 6. Why would I have warned us not to put in that extra edge from 1 to 6? In other words, that red edge right now. And that's one of the downfalls if you put in all of the numbers from your building set, all of your objects in from your building set too quickly, is sometimes you'll put in some of the edges that you don't need. So in this case, that red edge from 1 to 6 is actually one of our transitive edges, so we're actually not going to need it for the final Hosta diagram. So here's our Hosta diagram. In terms of a picture, it kind of looks like a diamond-shaped or a square on point. Okay. Now, if we then look at B2, did not want that in red, just a second. I'm attempting to have color here indicate what's the question and what's the actual work. All right, so B2 only has 4 objects in its building set, the empty set, sets of cardinality 1, and sets of cardinality 2. So we'll go ahead and build this one the same way that we built B3 in the previous example. Always put your empty set on the bottom. Why? Because in our partial order, things are ordered by set inclusion, so you do your smallest set at the bottom. Then you want to grab your next smallest sets, and here we've got 2 of them, just A and just B. And we saw previously that the empty set is a subset of every other set, so of course we'll put in the 2 edges going from the empty set to the 2 new sets. Last set involved with our building set B is the set of the two elements, A and B. And here, when we add in edges, we're going to look just at the sets that have cardinality 1, and both of them are actually subsets of that big set of cardinality 2, and we won't put in that transitive edge that jumps from the empty set up to the two element set. Now, these here include some scratch work, include the names, and we've now built the two Hosta diagrams for these two different posets. So what do you guys think? Are those two posets isomorphic or not isomorphic? These guys being relatively simple posets. You got it. So these guys are isomorphic. They have the same Hosta diagram right here. Notice the labels on the individual vertices right there are different. That's totally okay. If you wanted to write out the, whoa, stop doing that, program. If you wanted to actually write out the Hosta diagram without labels, both of these guys look like this structure right here. Now, what would we say? Our conclusion? Our conclusion then would be, therefore, poset D6 and poset B2 are in fact isomorphic to each other, and we'll actually be dealing with these posets that have this structure with subsets, or B with a different number on the bottom, and I'll tell you where that number comes from later, as well as these guys here that come from factors, or D with a various number. We already talked about where that naming convention came from. These are the two most common type of examples that I'm going to go over with us in this topic. But there are others, and in your book there's other ones that your textbook's author shows you for the homework too. Okay. But that's it for today. Next time we'll look at some other pieces and parts and then properties of posets. But that's the basics in terms of posets. If you understand what we did today in terms of posets, that's some of the main things that we deal with our posets. Everything else is just some naming conventions and some properties. Okay.